So guys, as I was saying, there are many flat partitional algorithms like K-means. K-means, as I said, is the most popular one. So now let's try and understand what K-means actually does, right? So K-means clustering is basically, as I said, K-means is the name kind of comes from this fact that it's a partitional algorithm. Because it's a partitional algorithm, flat algorithm, you have to kind of specify number of clusters that you want to kind of break the data into. In this case, K-means, as I guess the name kind of suggests already, K-means you are kind of breaking up the data into K clusters, right? So there are K clusters and you are breaking the observations into K clusters. That's why the name K-means. Now all we have to understand is, to understand K-means, basically what we have to understand is how do we, so the idea is very simple, right? For every data point that is there, we are gonna, so now let's try and understand the problem, right? So let's say there are x1, x2, x3, x4. There are 4 data points, and all we are going to do is basically, the idea is very simple. Basically measure the distance from x1, x2, x2 and x3, x3, x4, and all possible distances that you can measure. So say you measure it from x1, x2, and so basically it's a 4 cross 4 matrix, right? There are 4 matrices here, the points and the distances from each of them. And obviously x4 distance from x4 would be 0. So the idea is that in K-means we are basically, based on the distances that how you calculate, you are going to put them into different buckets, right? So if 2 points are very close to each other in terms of distance, then those points basically are points which are going to lie in the same cluster. If the points are very far from each other, they are going to fall in different cluster. So that's the understanding of K-means. So now, before we kind of get into the idea of into understanding what K-means is, let's first understand something which is called distance. So there's something that I'm already talking for now, which is basically distance, similarity. So this is a concept that I'm going, so points which are very similar to each other, and now I'm saying something called distance. So what is this? Basically this concept is same, right? So point which are very similar to each other have a very low distance between themselves. Point which are very far from each other basically have a very high distance. So let's first get the idea of distance cleared out, right? So distance is basically how similar the points are, right? So how close they are to each other. So lower the distance, similar the items, right? So now distance between 2 points can be measured in multiple ways. There are probably around 100 different odd matrices to measure distances between 2 points. What we are going to talk about some of them right now before we kind of understand K-means is basically there are a couple of distances. First is L1 distance, or what you call as the Manhattan distance, right? So Manhattan, so now let's say, to understand this clearly, let's say consider the point A1, A2, A3 and the point B1, B2, B3. So L1 distance between these 2 points is calculated as mod of A1 minus B1 plus mod of A2 minus B2 plus mod of A3 minus B3. That is one kind of distance. The second is L2, or Euclidean distance, and that is calculated as A1 minus B1 square plus A2 minus B2 square plus A3 minus B3 square and root over all of this, right? And then the final one is cosine distance. Cosine distance is calculated as A1 B1 plus A2 B2 plus A3 B3 by root over A1 square plus A2 square plus A3 square into root over B1 square plus B2 square plus B3 square. So this is the formula for calculating cosine distance, L2 distance and L1 distances. Once you understand this particular thing, right, this and there are probably multiple different variations of calculating distances. The thing to understand is when to apply which distances, right? So clearly you can see that this kind of a distance is something, L1 and L2 are something which are very highly optimized, or I would say pretty relevant matrices of measuring distances when you are looking at continuous features, right? If you have continuous features, this kind of values make a lot of sense, right? because you can kind of that's pretty awesome and exit. But now if you say if you have discrete features, and you would see if your discrete features are basically features which can have 1 0 values, right? So then kind of measuring distance using L1 and L2 would not be as effective, right? Because you would have 1 minus 0 or 0 minus 1, and there can only be 0, the distance between this value a1 minus b1, right, or a1 minus b1 square, that can only have two values, 1 or 0, right? And then you kind of add up, so then the possible number of distances, right, that between any 2 points is just limited. So those are the drawbacks if you are trying to use L1 or L2 distance in case of discrete distributions. Basically, when I say discrete distribution, I mean your x1, x2, x3, right? So x1 is basically composing of 3 features, x2 is a point which is represented as 3 features, and x3 is a point which is represented by 3 features. So if we represent all of them by 3 features, so if these 3 features are discrete within themselves, then it's probably not a good idea to use L1 or L2. Probably then a better idea would be to use cosine distance, right? So that's a kind of thing that I want you to kind of keep in mind while you kind of go ahead. There are also multiple other distances that you can have a look up. You can look up, Google yourself, or probably just read up the resources section. You will find more details around what are the different kind of distances that are there. But the idea is this, that there are multiple ways of calculating distances, and the kind of distance that you use depends on the kind of data that you have, right? That's the context about calculating distances. So obviously if you have some 2 points whose L1 distance say are very close, right, L1 distance is almost 0, obviously you can see that between the point and itself, right? So if instead of A1, B1, A1, A2, A3 and B1, B2, B3, I calculate distance between A1, A2, A3 and A1, A2, A3, so basically the point with itself, you can see the distance is 0, right, which basically means the values are very similar. So obviously values which are very similar to each other would have an extremely low distance, values which are very dissimilar would have a high distance. So that's the concept of k-means. Now k-means as a whole, the algorithm, now let's try and understand what k-means is, right? So to understand k-means, so all you are going to do is basically, the idea is, as I said, x1, x2, x3, x4, and then you have x1, x2, x3 and x4, and you can basically calculate the distance between each of them, right? So x1, x2 and something, x3, x4, something, right? You can basically calculate all of these distances. The problem with calculating distances between them is, so you find out x1 and x2 are close, right? And then you find out x2 and x4 are close, and then you find out x4 and x3 is close, right? So basically say you calculated the distances, let's say the distances lie between 0 and 1, right? So you say the distance in x1, x2 are close, so let's say 0.2, 0.8, 0.9, right? So these are the distances that you have. So obviously x1 is very close to x2. So x2 x1 distance is 0, x2 to x is already, now x2 and x4 are very close, so this is probably 0. Then this is 0.9, right? So this could very well be the case, right? So x1 is close to x2, x2 is close to x4, and x4 is close to x3, right? So this probably distance is 0.2, right? So this distances is less than 0.5, this is less than 0.5, this is less than 0.5. So you can kind of infer that this is the kind of scenario. Now in this case, you really do not know which points to club with each other, right? If you just look at the distances of points between themselves, so you would say, okay, x1 and x2 are clustered, but you then say, hey, x2 is also close to x4 and x4 is close to x3. So probably x1, x2, x3, x4 are all like in a single cluster, right? There's a problem with doing all of this, right? So instead of doing this, so obviously there's a problem with calculating distances of points between themselves. So in order to avoid that, what we do is we take x1, x2 and we take two fixed points, right? A and B. And then the idea is that we take distance of x1 from point A, say this is point 3 and this is point 8. Then from distance of x2 also from point, say the same thing, right? So in this particular case, you can see that x1 is close to A, so x1 is in cluster A. Then x2 is close to B, so x2 is here. x3 is again close to A. Then because this distance is lower, right? This distance is lower, this distance is lower, and then this distance is lower. So x4 is also in the same cluster. So this is the idea that we use for k-means clustering, right? So k-means clustering, the idea is very simple. I've already talked about distances, how you calculate them. Now for every point you basically take distances from two fixed points. Just understand this, why we use fixed points, because if we calculate distances from each other, we ended up with a problem where there's a cyclical reference. x1 is close to x2, x2 is close to x3, x3 is close to x4, x4 is, there can be a problem, right? So instead of avoiding that, what you do is you basically take two fixed points. How do you decide 2 points? Why not 3 points? That is basically how many number of clusters you want to divide into. In case you want to do 2 clusters, you basically say 2 fixed points. In case you want to kind of do 3 clusters, then you will have ABC points, right? So that's the idea out here. So let's say you have 2 clusters and you're going to do this, right? So you're going to take those 2 points and take the distance of each of the point from those 2 fixed points and see which is the least distance, and that is a cluster to which it belongs, right? Now, that is the whole concept of k-means. That's basically the thing that is there. All now you need to understand is basically how you calculate this point A and how you calculate this point B. What are these two fixed points? How do you find them out? As soon as you do that, that's kind of completing your understanding of k-means. All now we need to understand is basically how you do this whole process of finding out the values A and B. Now to do that, and that's first kind of get yourself accustomed with the fact that that's exactly what is missing out right now. We do not know how these points A and B are selected, but once we know that, then the rest of the algorithm is pretty simple, right? You basically find out what is close to A, and then you basically take that point, you put them in one cluster. If x2 is close to this point B, then you put it on this cluster. So this is your cluster A, this is your cluster B. Now how do you start off with the point A and point B, right? So these are two fixed points, right? So how do you figure them out? That's the only goal of this whole k-means algorithm. So to do that, that's pretty easy also, in fact. So this basically the whole problem, the way you do that is basically you start off with random points. See, it's pretty easy. You just, because you do not know what are those two fixed points are. So basically what you do is you start off with two random points, and then iteratively kind of keep on improving such that those 2 points resemble some fixed points, right? So I'm going to talk about that, what is the kind of iteration that you do. But the idea is that you basically start off with random points and then try to, as you kind of iterate over different iterations, you are kind of trying to minimize, you're kind of trying to improve upon your random guesses. That's the idea behind k-means. So now I've already told you what A and B are. A and B are basically fixed points, and your goal is to basically find those out fixed points, right? So you start off with random iteration, and every iteration you kind of improve that. That's the whole goal of k-means algorithm. We are kind of now, and only thing that you are still remaining to answer is how do you, obviously you start off with random points, but how do you kind of iteratively make that points A and B more better? What does making better even mean, and how do you do that? That's it. If you understand that, that's the only thing that is kind of remaining in this part. So k-means, so now I'm going to go and explain you what is there on the slides. So k-means in clusters in k-means basically follow two underlying rules, which is that cluster center is the arithmetic mean of all the points belonging to that cluster. So now if you can relate, in the earlier example when I talked about points A and B, those were basically cluster centers, right? So in this case, this was somewhere here. So basically if any point was close to this point, it's in this cluster, and if it's close to this point, then it's in this cluster, right? So for all those points in x1, x2 and x3, the problem was that basically you have this center, and what you have, this was your point A, right? And this was your point B. And the only constraint was that all these points in this cluster are basically closest to point A, then they are closest from point B, right? And for this point in this cluster, they are closest to point B than they are closest to point A, right? So distance from B is basically lower than distance from point A, and point A and point B are nothing but basically a mean, right? So that kind of completes the entire understanding of the algorithm for us. So now I'm going to explain you how the algorithm works in a very simple way. So what you do is basically you start off with random points. So you start off with random points. So this is random, 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 and you start with random points, right? And then you do this whole thing, right? So then you come up with two clusters. Say this is the first step iteration. So you have 2 points out here, and say somehow you have 2 points out here. Now you calculate the average of these 2 points and you find out the average of these 2 points. Now for this is your now new point A, now this is your new point B. Now assuming that this is your new point A and new point B, then you again do this iteration, right? You go back here. And then you kind of again redo the cluster. So now you come up with this thing that this is one point and this is there are 3 points out here, right? And then based on that you again have your new A, new B. This is your new A, this is your new B. And then you again go back here and then you again come back here, right? So that's the whole goal of this algorithm. That's exactly what K-means is all about. So now you kind of completely understand, right? So at each step you first start off with random points. At random points you basically see based on this random point initialization, you see which are the points which belong to this cluster, which are the points which belong to this cluster. Now based on the points that actually come here, you basically then recompute the mean of those 2 points, right? Yeah, in this case there were 2 points, so you calculate the mean of these 2 points and that is your new cluster center, and you calculate the mean of these 2 points and this is your new cluster. Now these are your new points A and B. You go back and do this whole assignment process again, right? So there's a one process. So this process is basically there's one step here and there's one step here, right? So there are names to these particular steps. I'm gonna talk about that in a while, but there are clearly 2 steps, right? The first part is you assign each point a cluster. Once you do that, calculate the cluster mean and then again do this process, right? So there's a cluster mean calculation step and there's a cluster assignment step. That's it, right? So cluster mean calculation step and cluster assignment step. So you kind of revert back, and how long kind of you do this? Say the same thing, right? If in the next iteration also you see that these 2 points are basically belonging to the same cluster and these 2 points are also in the same cluster, right? They are in one cluster, they are also in another cluster, they are in a separate cluster. So this is an independent cluster, this is a different cluster. Then you say that okay, probably that means my points, the cluster membership of these points are not changing, right? So that probably means that I can stop this process, because there's no point of doing that, because now you will again calculate the mean and the mean would basically be the same. So as long as the mean, the point A and B are not changing across iterations, you kind of if that is the case, if it's not changing, you say okay, I think enough iterations done, I have reached my final conclusion. So this is the whole idea of K-means algorithm. There are 2 steps, you kind of iterate between them, and your goal is to basically make sure that these points A and B are the best chosen points. How do you do that? You first start off with random points and then each iteration you assign points a cluster and then calculate mean. Again go back and assign cluster, come back and again assign mean. So that's the thing. So now let's understand obviously in a particular detail. So K-means is a optimization problem. So I have already talked about, I have not probably talked about the mathematical details as much. So I'm going to keep it simple for you guys. Don't get so bothered up about it. So what K-means does is basically it's trying to minimize the distance of each point from its cluster center. Now you go back and you see there, right? So there were 2 points. So all it does is basically when you have finally done this calculation, right? So you have a cluster, say there are 2 points here. So this is a cluster center and this is a cluster center. All basically it is trying to do is basically minimize the distance of points from their cluster center. So if it's belonging to this cluster, then this distance plus this distance plus this distance and square. So all that your cluster K-means algorithm is basically trying to do is basically it's just trying to optimize the distances of each of the points from its corresponding cluster center. Obviously the lower this distance, the better the K-means algorithm, right? And this is a NP-hard problem. What is a NP-hard problem? NP-hard problems are basically 2 kinds of problems. 2 kind of criteria kind of apply to NP-hard problem. The first criteria is basically that your algorithm should be it's very tough to kind of find a solution to your problem, but given a problem given a solution you should be you should be able to verify very easily if the solution is correct or not, right? So this applies NP-hard, most of the optimization problems, famous tough NP-hard tough optimization problems like traveling salesman problem, or in case of K-means you see. So the idea is the same, right? It's very tough to kind of come to the theoretical solution, but given a solution you can very easily come and check whether that solution is correct or not. And the second part of our NP-hard problem that defines the NP-hard problem is the fact that the amount of time complexity of the solution, basically the time and the resources taken to kind of compute the solution, goes exponentially high as your number of, say in this case, number of, say, clusters, right, n clusters, number of clusters you want to break into. As that n increases, your amount of time taken to solve that problem increases exponentially. So those are the two criteria of NP-hard problem. You cannot find a solution, but you can easily verify if that solution is correct. The second is the amount of time taken scales exponentially as the complexity of the problem increases. So that's it. So now, as I said, K-means is basically you solved using a iterative step of algorithm. This is a class of algorithm called expectation maximization step. So the expectation maximization step has basically two steps. One is expectation step, which is assign points. The second is set cluster centers to mean. This is something I have already told you. This is basically the E step. This is the M step, right? So expectation step, the maximization step. So that's E step and that's the M step out here, right? So once you do that, that's exactly what is going on out here. So I've already explained you how this algorithm works. So I've already explained you all of this. So now let's go to the GIF and understand that better. So this is your GIF. So you have the distribution. You first start by random points, C. Then you assign clusters. And now you're going to recalculate the mean. See, now those black points are now new means. Now you're again going to calculate, assign clusters, calculate mean. Now you're going to again assign clusters, calculate mean, and you see that there's no change in the points. So that's when you stop iteration, right? So that's the idea. It's very simple. You look at the GIF yourself. So again, you start by random, I initialize, I've already talked about, so there's not much. So now in this case, you can see that how this GIF basically kind of gives you an example of how random initialization started, and then how that kind of, you have the different cluster means. They started off randomly, and you can see how they kind of over different iteration slowly stabilize into the equilibrium position, right? So you can see this is a random start, and then it kind of slowly it kind of stabilizes. So popularity of K-means, right? So K-means is extremely popular, as I was saying, right? There are multiple variants of K-means that comes along. So there's a K-means, there's a K-means plus, which basically changes in the way initialize, instead of random initialization, slightly more intelligent initialization. There is a K-medioid, which instead of calculating means as cluster centers, as of now I was always saying cluster center is basically calculated as the mean of the points in that cluster. So instead of calculating mean as the point, you take medioid, and there's all sorts of those kind of different variations, right, that you can do with that. How you calculated distances, there are a lot of variations to different variations to the main algorithm. But the main algorithm, as I've already explained to you, is very simple. It has two steps: the assignment step, the calculation, mean calculation. In assignment step, you are calculating distances from both the means and seeing which cluster each point belongs to. Now for that particular assignment, you see that what is a new mean. Those are your new means. Based on that, you again do the assignment. As simple as that, nothing much here. So now I'm going to explain you how that works in sklearn. So sklearn, obviously you first import it, then you do the whole dataset loading, then do the test train. Only thing is now anymore, so earlier in scikit-learn we had x, we had a y, and then we do dot fit x comma y. Notice here we are not anymore doing that. We are just going to stick to dot fit x, right? Because this is unsupervised learning. There is no more target data to kind of deal with. So that is the labels that you have. So km.labels is basically the corresponding. So when you do dot fit and then you do dot labels, what you're getting is basically for each point in that training data, what is the corresponding cluster that has been assigned to it. There's a cluster 0 which is assigned to it, cluster 1. Please note that this 0 and 1 has no relation at all whatsoever with your test data. In your test data, you might have label 0, 1, right, and all of that thing, right? Say you're trying to do you're trying to do this problem where you have the applicants of a loan and you basically figure out whether they should be given a loan or not. So that's your y data, is y value, which is your target value, is basically 0, 1, 0, 1. Now if you take the x and you kind of cluster it into two categories, you really do not know which is the, obviously km.labels would give you that there's a 0 label cluster and there's a 1 label cluster. Now just keep that in mind, that the 0 label cluster does not really mean that it's the 0 target value, right, of your actual data. So basically in your target data, I'm not sure if I'm kind of clear enough here, but let me kind of try and approach this in a different way. So in your target, in your real data, you had basically the labels which said that if it was given a loan or not. And if it was given a loan, it's a 1. If it's not given a loan, it was a 0, right? So that's your y values. Now you take your x values and you just do clustering. So you will get basically which points belong to 0 label cluster, which you get to 1 label cluster. Now 0 label cluster does not necessarily imply that those people were not given loans. It could probably be also the cluster where people were actually given loans, right? Because the algorithm doesn't know what is the y values. It just basically gives a random number as a cluster label. So 0, 1, 2, these are just labels which basically say that okay, 0 label. So basically all points which are at 0 level are basically very similar to each other. All points which are in 1 level are very similar to each other. Whether this 0 and 1 actually has any significance in physical world is something you have to check, right? All it is saying for now is basically that points which are basically labeled as 0 are very similar to each other, points which are labeled 1 are similar to each other, 3 similar to each other, points which are labeled as 4 are similar to each other. That's all it is, right? There's nothing more into it. So just don't try and interpret it as okay, so probably this is a 0 class prediction or 1 class prediction, nothing. It just says that this label points are very similar to each other. So these are the different cluster center. We tried dividing them into 4 clusters and you can clearly see that yeah, we had 5 clusters, right? So we can clearly see that there are 5 clusters out here. So now you do km.predict. So this was your first data point and you kind of do km.predict. It gives you which is the cluster it belongs to. Again, this is as per the random assignment of labels, right? So just because the array says 1, that just means that everything that also is of label 1 are very similar to this particular point that we have chosen. That's about it, nothing more, nothing less. Now we are going to add some synthetic data and we see how k-means plus performs, right? So we're going to add some Gaussian distribution data and we are going to have distribution from two different data from basically 2 different distributions. So which is my point A, basically the points from the points which are marked under the variable A and the points which are in the variable B, right? So those are drawn from 2 different distributions and finally my X is basically a concatenation of those 2 points. I combine those 2 points. The idea is that can my k-means give me 2 different distributions, right? If I just try and divide this whole x is basically combination of A and B. Ideally, we know that A and B manually we have selected it from 2 different distributions. So ideally, we would expect the k-means algorithm to kind of separate x into the bucket A and bucket B, which will ideally it's supposed to happen that way, right? So let's see if that happens or not. So this is the data. As you can clearly see, there is visually we can clearly see there are 2 different buckets out here, right? So now let's see if k-means can separate that out or not. Also apart from that, we have done something else. So apart from those 2, we have added 3 more distributions. You can see a C, D, E, right? So now you can see x2, x1 was your x, right? X was your original distribution and now on top of that you have added 3 more distributions from 3 different basically 3 more distribution sample values and now you can clearly see 5 different kind of buckets, right? So we have just basically added 5 different buckets. The idea is to test if k-means is working well or not. So now when you do k-means and we pass cluster equal to 2, right? So this was the first case where we had just 2 distribution. We have data from 2 distributions and you can clearly see that actually this is probably working pretty fine. So this was the second case where we had 5 distributions and we did again passed number of clusters equals to 5 and we see this did a fantastic job out here, right? So that means we kind of can be sure that k-means actually work, right? Because we had 5 distributions. We artificially synthetically generated those data distributions and we generated the synthetic data such that we knew already before and they were from 5 different buckets. The idea was we put them together and gave it to k-means and saw, and we were trying to see if k-means kind of gave out 5 different buckets or not. That clearly happened. So we can trust that k-means is working pretty fine. But definitely not everything that looks awesome. Nothing in data science per se is like awesome. There are obviously good things and then there are bad things, the pros and the cons. So k-means definitely has a lot of shortcomings. It's the most popular, don't get my word wrong, it's definitely the most popular one. But then it has different shortcomings that we are going to discuss here. So the first up is problem is that global optimal result may not be result. You know that step, right? We do not know the mean, so we iterate. So we assign, and then we calculate mean, assign and calculate mean. We do that, and by doing that, we know that the globally optimal result, right? The globally best possible result may not be optimal. We might run out of iteration, or it might take a lot of time to kind of the means to kind of stabilize. So that's a problem. So that's why you basically use so it's very much dependent on where you start off. If you're starting off a very far distant point, then it would obviously take you some time to stabilize. So that's why there are intelligent initializations that you can do. Random, instead of random initialization, you do still random, but in a slightly more advanced way, such that you kind of make sure that you kind of guarantee that you kind of at least come very close to convergence, right? So that's the first problem that we are discussing, which is the shortcoming. And the result is basically using something called K-means plus. K-means plus is basically nothing but better intelligent initialization. So next is shortcomings, is that you have to kind of specify number of clusters that you need to number of clusters that you expect, right? So for that, in our case, when we had 5, we had composed data from 5 different distributions, and we put them together. We knew that they had come from 5 distributions. That's why we passed n clusters equals to 5. In most of the cases, this could be a case. You might beforehand know that you want to, and you know that there are 5 different kind of customer segments, or you know that your number of articles that you're kind of segmenting into, right? The news articles, they come into sports, tech and political buckets. You know that there are 3 buckets, but it may not be the case also, right? You probably do not know beforehand how many buckets are probably possible. So in that kind of a case, K-means is a bit tricky, right? Because you cannot really say what you have to initiate before. When you start the algorithm, when you have to kind of initialize the algorithm, you have to say number of clusters that you want to kind of separate your data into. And if you do not have a beforehand idea of that, you can still kind of solve it. Let's see what you do. So the idea is, you basically same as what we did for hyperparameter tuning, right? So what we are going to do is basically try for all possible different cluster sizes, right? So we try for cluster 2 cluster, 3 cluster, 4 cluster, 5 cluster, and for each of them we basically see how well the cluster has been formed. Now how do we check this, how well the cluster is formed, is basically using this particular thing called inertia. Inertia is nothing but basically sum of the distances of points from their cluster, the distances of each of the points from its corresponding cluster center. Sum of all the distances of each of those points from the center is what is called inertia. Basically we want the inertia to be as less as possible, right? Because that's what K-means set out. If you remember, the whole objective of K-means was basically to minimize this particular thing, which was basically sum of the points from its center, cluster center, and that's exactly measured by inertia. So basically we do this, and we see that the elbow is, there's a lot of inertia initially, but once you kind of go to 4 and 5 onwards, you can clearly see that the inertia is pretty low. So you can kind of settle down for any value which is higher than 4, right? As you can clearly see, the inertia is pretty high when the number of clusters are low, and kind of gradually goes down. You can see that there's an elbow at 2, right? So basically it means that as soon as you have 2 clusters, the model is much better, right? The inertia is much lower. So you can probably choose 2 or 3 or whatever around that as a optimum number of clusters. But this is only under the assumption that you don't have an idea of number of clusters that are supposed to be there in the data. If you know that, well, go ahead and do that, right? Because you already know what are the number of clusters to separate into. So this is the same thing, and you can clearly see in the elbow up method, you can see that in this particular case for 4, you can probably, if n clusters equals to 4, you can probably see a sudden drop in inertia at n equals to 4, right? Number of clusters equals to 4. So you can probably say that, okay, if for 4 clusters, I think this data, 4 clusters, I think that probably makes a good sense. So next is K-means is limited to linear cluster boundaries, right? So why is that the case? So let's try and understand that. So in this particular case, what you're doing is, so for any point, you're saying there are 2 points A and B, and you're going to measure the distance of x1 from A and B, and so this is A and this is B. So for A and B, you're basically for each point you're going to measure the distances from A and then B and see which is the distance which is the lowest, and that's the corresponding cluster it gets assigned to, right? So now if you understand that a bit more detail, so basically what are the points that are lying on the boundaries is basically this particular points, right? These points which are equidistant from both A and B. Those are the points which are basically, this is a point B, right? So this is a point A and this is a point B. Now for each of the points that are equidistant from both A and B, you can clearly see that those are the points which basically form your cluster boundaries. And as you can clearly see, what is this particular line, right? So this particular line is basically nothing but the perpendicular bisector of this line, right? So all points lying on this particular thing is basically are points which are equidistant from both point A and B, and that's why in case of K-means you basically have a linear boundary, because your boundary basically represents nothing but points which are equidistant from 2 points, and we know that from geometry, as I said, that locus of a point which is equidistant from 2 other points is nothing but a straight line, right? So that's why K-means is just limited to linear cluster boundaries. If you have non-linear methods, probably, as you can clearly see in this case, right? So sklearn is something that would not probably work as good in this particular case, because clearly there is a non-linear boundary that is required to separate these two particular clusters. So in this kind of cases, K-means probably would not do a good job. So way out of that is basically using something called spectral clustering. Probably you can read up the details a slightly bit later. The idea behind them is basically you project the data into a higher dimension and then do clustering such that in a higher dimension they are linearly separable. This is the same kind of concept SVM uses, right? So this concept is very similar. You kind of project into a higher dimension such that they are linearly separable and then cluster them in that particular dimension. So in that dimension, as you can clearly see, if you do spectral clustering, you have been able to easily segment this into 2 different clusters, right? So now finally, so obviously inability. So I have obviously talked about the different shortcomings of K-means, and now final option is the final shortcoming that we're going to discuss how it is. K-means can be slow for large number of data sets. Obviously, if you can understand there is the expectation step where you're kind of assigning each data point to a particular cluster, then calculating cluster means. So obviously number of data points, if they are large, probably this could be really bit slow. But then it goes also without saying, for a large data set, frankly, all other clustering algorithms that you're going to look at least in the lecture, the other kind of thing which is hierarchical clustering, which we are going to discuss after this, that is in fact like way more time consuming than this thing, K-means, right? So K-means is expensive definitely for large data sets, but other algorithms are definitely even more expensive. So yeah, so there are different ways to kind of even make K-means much better for large data set. So the concept is called mini batch K-means, where basically you take, instead of taking at each step, right, where you're kind of assigning labels, instead of doing it for all the data points in that particular data set, you're gonna do it just for batches of 5 or 10 probably. You just do it at every step. Every iteration, you do not do the entire data set. You do not look at the entire data set and assign each of them again labels. All you're gonna do is look at chunks and assign them labels, and then again do the calculation in chunks, and then go again and do the expectation step in chunk, maximization step in chunks. That's the idea of K-means batch, mini batch K-means. That's the way you kind of make sure that even if there's a lot of data, K-means kind of does pretty good, right? But that's obviously, I've already told you, there's a disclaimer out here, which is that it's expensive definitely, but even other algorithms are way more expensive. So K-means mini batch K-means is basically just a way to kind of make sure that even whatever amount of time it was already taking, to kind of make sure even it doesn't take that much time, to kind of make it easy for K-means even when there's a large data set. So obviously now that we understand what is K-means, now let's try and go and understand the last part of the section, which is hierarchical clustering.
Log on to Grey Atom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.